Now for this next page, page 115, you will need graph paper, and I've provided graph paper in the assignment, so you can click on that link and download the graph paper, or you can use your own graph paper. But the key thing is we're going to make a graph, and we're going to plot the decay curve as well as a radiometric growth curve, right? So you'll have access to the graph paper. Then on the x-axis, we're going to have the number of half-lives. And then on the y-axis, we're going to have the atoms, the parent atoms that decay, and also the daughter atoms that are going to grow, right? So what I've done, I've already made a graph here. And you can see on my graph that on the x-axis down here, I have the number of half-lives elapsed. So at time 0, there are no half-lives. That would be 1 half-life, 2 half-life, 3 half, 4, and so on, right? And for the y-axis, I have the parent atoms, right? So I start off with 1,000 up here, and then I go down to 0 here. And the way I've done it, if you're using this graph paper, I've made every inch or every 10 boxes a half-life. So I can fit 10 in here. You can see I could fit 10. But over here, I couldn't quite fit 10 for 1,000 parents here. So what I've done every 6, just to kind of expand it a little bit more. So every 6 boxes is 100 units. So it goes up to 6 inches, which is going to be 1,000, right? And so so every 6 is 100 units. So you can kind of space it out that way. And then I created this graph here. And so the next thing it's asking you is that the half-life of this element we're gonna plot is for carbon-14, because carbon-14 decays in nitrogen-14 in 5730 years. So every 5730 years, 1 half-life elapses, right? And so in this case, we're going to actually put those numbers on the half-lives. So I've already done that over here. So at 0 half-lives, note that there are no half-lives elapsed. But then after 1 half-life, well, it would be 1 half-life, which is the half-life times T1 half. Remember, T1 half is 5730 years. So 1 times 5730 is 5730. And then after 2 half-lives, I'd put 2 half-lives elapsed times 5730 will give me 11,460. So I just do that. For 3 half-lives, it's 3 times 5730. For 4, it's 4 times 5730. And that's how I can get these numbers. And eventually, when I get to 10, well, 10 times 5730 is 57,300, right? So that makes sense. I just move the decimal place over there. So you want to add those in there, the half-lives or the age of the sample at these different half-lives, right? Using the carbon-14 T1 half, which is 5730 years. Then the next thing they ask us to do is to, at each point, label the number of parent atoms there are and the number of daughter atoms. And I did the first one here because they're going to ask us a question about half of a half-life here, because this, at this point here, it'll be 1 half of a half-life, right? So at 1 half of a half-life, I'm going to have 275 daughter atoms, but I'll have 750 parent atoms, right? At 1 half-life, I'm going to have 50-50, 500 parents, 500 daughters. And then as I decay to 2 half-lives, I'm going to have 250 parents, and I'm going to have 750 daughters up here. Let me zoom in a little bit. And so this kind of continues on. So all I'm doing now, to get to this one, I just took 500 divided by 2, gave me 250. And then, which means that other 250 I had to add to the 500 to give me 750 up here, right? So now I'm down to 250 parent atoms. I divide that by 2, I get 125 parent atoms. Well, I take that 125, add it to 750, I get 875 up here, right? So that's kind of what I'm doing here. Now I'm down to 125 parent atoms after 3 half-lives. Divide that by 2, it gives me 62.5. So 62.5 plus 875 gives me 937.5. So anyways, this is how I'm doing. I'm just cutting it in half and half. And note that I kind of stopped over here. I didn't even do the 9 and 10, is because they're not going to really ask us any questions. So if you can just go at least out to maybe 8 half-lives doing, here I have 3.9 parents and 996.1 daughter atoms, right? So I put the 996.1 up here. So anyhow, that's our decay curve, and this would be our daughter growth, right? So in the end, you should show both curves, the decay of the parent and the exponential growth of the daughter product. And then once we've established this graph, you're going to submit this. You're going to either take a picture of it or scan it and submit it with the assignment. you're going to answer these questions. So, for example, question 8 is asking, how many years are equal to 5 half-lives? Well, we've already so here's 5 half, that'd be 2860. So you would write out 2860 right there. And then for number 9, how many parent atoms will be left after 5 half-lives? So it would be, in this case, it's 31.25. 31.25 would be the answer that you'd put there. And then for question 10, how many daughter atoms are after 5 half-lives? So for the daughter atoms, you see it's 968.75. So you'd put that in there. So basically that's what you're doing, just answering these questions by using your graph, right? So for 11, at what point in time, number of half-lives, will the number of parent atoms be equal to the number of daughter atoms? So the only place they're equal is right here, right? And that would be at 1 half-life, right? That would be at 1 half-life down here. So you kind of work your way down here. Remember, for question 19, carbon 14 decays into nitrogen 14. And then you can answer these questions. And questions 22 and 23 deal with half of a half-life over here. And so then you can do the calculation to give you the age. So basically it'll be half of that number right there. So this should be pretty straightforward. And what's nice about a graph like this, you can use it for any isotopic system, because the decay and growth of isotopes during radioactivity are going to be very similar. So for example, we know that for carbon 14 going to nitrogen 14, the T1 half is going to be 5730 years, right? So so remember, we can't really date anything older than about 50,000 years for this one, and also had to have been alive. So, but we can also use it for volcanic rocks or igneous rocks. And for example, potassium 40 decays to argon 40, and its half-life is about 1,300 million years, right? And so in this case, you would just take that 1,300 as a T1 half and just substitute the numbers here. So it'd be 1,300 here. It'd be 2,600, so 2 times 1,300, and so on, right? So you can see that it gets quite old pretty quickly here. But anyways, you can use it for that system. Remember, 238 uranium decays to 206 lead, and the T1 half for that one is 4,500 million years, right? 4,500 million years. And the other one is 235 uranium decays to lead 206 or 207, lead 207, and that is about 714 million years for the T1 half on that one. So again, you can use it for any isotopic system. It will be kind of the same curve. And we'll be using a couple of different methods for isotopic dating, as you'll see in the next slide here. All right, well, let's stop here for now.